Hello, everybody. This is Dr. Tracy Toops. I am here to give a nice little supplemental lesson on poles and zeros because I did not make it to the very last section lecture because I was sick last week. So let me go ahead and share my screen real quick, and it won't be too long, maybe 10 or 15 minutes. I'm feeling mostly better, so don't worry about me, guys. Oops. Let's move some stuff around. Okay. So just to give a recap, the last thing we did was, and we're talking about all these 4 different roots, which we finished about right here. So 12.8 poles and zeros, we kind of already talked about a little bit before, but we'll make it a little more formal, right? Pretty much any function we have that we used before is polynomials, right? You have a certain order n on top and certain order n on the bottom. In this case, this is n to the 4th on top and the 2nd on the bottom, right? You end up finding roots for everything, and these roots are actually very, very important in terms of circuit analysis. For example, let's say this whole function right here was an impedance of a circuit, right? So in our case, let's say we had a voltage source. There's a current going through it. We had a Z network. We don't know, we're not really sure what this is. It could be a large filter, it could be a complex cellular network, who knows? And there's current going in, right? V of S, I of S, right? To figure out how much current going through, we're going to use impedance, right? I of S is going to equal to V of S over Z of S. Now, what's very important and let's say this is a network where frequency will vary, right? Like a cell phone. Remember, cell phones, because you're using wireless, is going to have all sorts of different frequencies, right? All the way from maybe 1,000 hertz to, I don't know, 100 gigahertz or something, right? So the question is every time you change a frequency, because there's inductors and capacitors in the circuit, your impedance is going to change. That's what filters do. So here, when you start looking at this equation, this is the resultant impedance of this circuit, right? You could figure out your poles and zeros by looking at your roots. Roots are very important because for every root in the denominator, right? If you set, let's say we know one root is s equals -4. If you set s equals -4, you can get a 0 right here. So you're going to do a number divided by 0, right? So you can get an infinite, 0 right here. You can get an infinite impedance. So this impedance at this s equal -4 went to infinity. So your output is open circuit. Conversely, you could ask the same question and say, well, what about a numerator? If we set s equal to -10, we're going to have a 0 right here. So you can have a number divided by 0, and this whole thing's going to be 0. So in that case, this is a short circuit. Short circuit, open circuit, right, for infinity. So those are 2 very extreme edges that are very important in circuit analysis because a short circuit, you're shorting the impedance, so you're going to overburden your circuit. And open impedance, you're not doing anything, right? So these points are important in circuit analysis as key design factors, so we need to pay very close attention to where these poles and these roots happen to land on. And it'll get to the point to where eventually when you start building filters later on and doing, let's say you go to communications, you can actually choose these values carefully, these roots and poles, to design a specific network to do what you want it to do. For example, FM radio, if you wanted to clearly tune in on a specific frequency, then you need to change these roots to make sure that happens. And eventually you'll learn that there is a cause and effect in the number where you place your roots versus what your circuit topology will look like. Okay, so to group them up, there's 2 groups of roots. You're going to have one on top and then one on the bottom. Okay? The ones at the bottoms are called poles, right? One easy way to think about this are poles because they make your circuit go to 0 on the bottom and infinity on top. So then you're going to have an asymptote. So it kind of looks like this, right? So it goes all infinity and comes back to negative infinity like that. So imagine that there's this giant pole in the middle, right? And that's where your pole comes from. It's because it creates an asymptote, which is a pole, right? Conversely, the top part, if you set those, so those specific values to set the top to 0 are called zeros because they zero out the circuit, right? Meaning the whole thing gets set to 0. So that's where poles and zeros came from, right? In this particular case with this circuit that we're looking at, we know we have a S equal -5 and -10, right? So one nomenclature they like to look at is they like to put everything in -Z1, -Z2, -Z3. There's a little pattern for this they won't like to do, as we'll see later. For now, that's what you need to know, right? So in this case, this Z1, right, is -5. And then this Z2 equals -10, right? And so and for the poles for us, sorry, they say right here, the zeros for FS are -5 and -10, right? The poles, P1, in our case, we just look at all these 4, right? They're going to be -1, P2 is going to be -2, P3 is going to be -3, P4 is going to be -4, right? So basically, once you do your circuit analysis, get your big your big function right here, your transfer function, then you do your split up in your individual roots right here. So you get your roots out. This is where you can figure out all your poles and zeros, right? Again, poles on the bottom, zeros are on top, okay? So coming over here, that's done. You could go a lot bigger, where here you have a more complex function, right? In this case, we have imaginary poles and zeros, which are perfectly fine. You will see those, right? So all you gotta do is just keep track of them. One handy thing is you can always plot it on the XY plane right here. This is your imaginary part. This is your real part. And notice because all our poles and zeros are negative, they're going to be on the second and third quadrant, right? Pretty much all poles and zeros should be negative in the end of the day, right? If you ever have a positive pole and zero, they're going to be on this side, right? Typically, it's pretty bad. You almost know, and once you learn controls engineering, they're going to say typically on this plane, you want everything on the left-hand side. If you have anything on the right-hand side here, it's going to be unstable circuit, and you're probably going to blow something up. Okay. Now, in this particular case, let's kind of erase it a little bit. You have one pole, 1 0 at S equals -5, +3, -3 plus J4. And of course, you can have your conjugate pair, which is -3 minus J4. So you could go over here and plug in, put little circles. Every circle here, so here and here are going to be zeros. Circles are zeros. Note you got -5 on the axis, and -3 plus J4 and minus J4. So remember, conjugate pairs will always come with pole pairs, we call them, right? And then you could go ahead and, zero pairs, what we're talking about. Looking on the denominator, here you got a 0, a pole at 0, a pole at -10, and these two conjugates. So first off, the 0 one's easy. You put a cross at the 0 crossing right here. You go -10, put another cross. And then in this case, this is -6 plus J8. And then the other one will be -6 minus J. So you can go -6, -8, and up here. Okay. So eventually you'll get to a point to where you can just read this graph and kind of know exactly what's going on, right? In the end, I mean, how can I say, once you get controls engineering later on, this will be very, very important. Right now, this is a very basic introductory course. I just want to kind of show you, hey, these are where the poles and zeros are. right? Again, remember, a pole is whenever your function tends to infinity. A zero is when your function tends to zero, right? So whatever voltage, current, impedance you're representing, these poles and zeros are very important, okay? Kind of, for example, let's say number one, you got a circuit, right? Step two, you would do analysis, right? Figure out and then do your Laplace transform of what you want. So you can have a single function, be it voltage, current, impedance, right? Figure out roots. And from there, 5, you can find poles and zeros. Note that this is before doing any inverse Laplace transforms, because honest to God, a lot of times when you do engineering, once you get to this point, you're done, right? This gives you enough information to know how the circuit behaves. To do the inverse Laplace transforms if you ever want to go back to the time domain stuff. And I'll be honest, most of the time, I mean, you got to learn it now because it's circuit analysis. But a lot of times later on, once you get to the poles and zeros to step 5, that's pretty much it. You're done with your circuit analysis. You can literally take this circuit and this graph right here and pretty much map out how the circuit's going to behave later on. Okay. So that's pretty much it about poles and zeros. There's a couple of homeworks to show you what's about. There will be an exam question on poles and zeros, so please pay attention to this and go through it all, okay? So I think that's about it. Let's go and clear our drawings. You guys got any questions, let me know, and I'll be here on email over the weekend. All right, so you guys have a good day.